Welcome back to Mr. Vaughn's classroom. Before we get started, I'd like to ask you to please hit the subscribe button and give this video a thumbs up. Today we're in Unit 5, Introduction to Exponential Functions, and we're looking at Lesson 13, Reasoning about Exponential Graphs, Part 2. The learning goal today says let's investigate what we can learn from graphs that represent exponential functions. We have two learning targets today. I ask you to keep these learning targets in the back of your mind as we work through the practice problems, and at the end of the lesson we'll come back and look at them again and make sure that you're prepared moving into the next lesson. Learning target number 1 says I can explain the meaning of the intersection of the graphs of two functions in terms of the situations they represent. Learning target number 2 says when I know 2 points on a graph of an exponential function, I can write an equation for the function. And we have one glossary term for this lesson, and that is exponential function. An exponential function is a function that has a constant growth factor. Another way to say this is that it grows by equal factors over equal intervals. For example, f of x equals 2 times 3 to the power of x defines an exponential function. Anytime x increases by 1, f of x increases by a factor of 3, meaning that every time x increases by 1, you're multiplying by 3 to find y. Now we can begin the practice problems for Unit 5, Lesson 13, Reasoning about Exponential Graphs, Part 2. Here is a graph of P, an insect population, W weeks after it was first measured. The population grows exponentially. Number 1, what is the weekly factor of growth for the insect population? Now previously, they had always given us 2 points that were consecutive, and we could simply divide the second y by the first y to find the growth factor. But now they're raising the difficulty a little bit because the points they give us are not consecutive. So now what we need to do is we need to take the information we have for each point and we need to fill out the exponential equation using that information. And what we're going to do is we're going to have the equation for the second point, and we're going to divide it by the equation for the first point. For example, we know that y equals 8,100 on this second point. We do not know what the initial amount was, and we do not know the growth factor, but we do know that x is 3. Now we will do the same thing for the first point. We know that y is 900. We do not know the initial amount. We do not know the growth factor, but we do know that x is 1. So we have 8,100 divided by 900. That equals 9. We have A divided by A, and any time you divide something by itself, that is just 1. Then we have B to the third power divided by B to the first power. And when you divide with exponents, you subtract the top exponent minus the bottom exponent. So this becomes b squared. The opposite of squaring something is taking the square root. So we have the square root of 9 equals b. And there's two answers here. The square root of 9 could be -3, or it could be +3. If it was -3, then we would be having a downward exponential graph. But this one is going up. So we know that b is going to equal +3. So the weekly factor of growth is going to be 3. Number 2. What was the population when it was first measured? Well, we know that after 1 week, the population is 900. So if I want to find the population 1 week earlier, and I know that the growth factor was 3, then I can take that 900 population after 1 week, I can divide it by the growth factor, and it will tell me that the initial population was 300 insects. And number 3, write an equation relating P and W. Well, P is going to equal the initial amount, which we said in number 2 was 300 insects, times the growth factor, which we said in number 1 was 3, to the power of the input, which is W. Now, if you told me the number of weeks, I could take 3 to the power of the number of weeks, multiply it by the initial population of 300 insects, and it would tell me what the population was at that time. If you have any questions about how to solve a practice problem like this, please leave a comment below, and I'll get back to you with any assistance I can offer. Our next practice problem says here is a graph of the function f defined by f of x equals a times b to the power of x. Select all possible values of b. So we need to understand that b is the growth factor. This is the number that we're going to be multiplying by each time. And we need it to result in a graph that is decreasing. So this is exponential decay. So the first choice is 0. Well, if I multiply by 0 over and over again every time x changes, I'm always going to end up with a y value of 0. So this would actually result in the x-axis. As x is increasing, y continues to be 0. So that does not match. The next option is that we're multiplying by 1/10 every time. Well, if we're multiplying by less than 1 every time, then our answer is going to keep getting smaller each time. And that's what we see here. So B would result in exponential decay. So B is a correct choice. The next option, C, is 1/2. If we multiply by 1/2 over and over and over again, that y value is going to keep getting smaller. This would result in exponential decay, which is what we see. So both B and C are correct answers so far. The next choice, D, has a growth factor of 9/10. This is less than 1. So if we keep multiplying by 9/10, the y value will keep getting smaller. So this does represent exponential decay. So B, C, and D are all possible solutions so far. E says we're going to have a growth factor of 1. Well, if I continually multiply by 1, then my y value is never going to change. It's going to stay whatever the initial amount is. So this would actually result in a horizontal line. And that's not what we have. So E is not a correct choice. Next, F says we're multiplying by 1.3. Well, if I keep multiplying by 1.3 every time, then my y value would continue getting larger, and I would see exponential growth. We don't see exponential growth in this graph. We have exponential decay. So F is not a correct answer. And the last option, G, is 18/5. Well, 18/5 is the same as 3 3/5. This means we're multiplying by more than 1 each time, so the y value would continue getting larger. This would also result in exponential growth. And our graph shows exponential decay. So G is not a correct solution. So the only options that result in exponential decay are B, C, and D, because that has us multiplying by a number somewhere between 0 and 1, not including 0 or 1. If you have any questions about how to solve this practice problem, please leave a comment below, and I'll get back to you with any help I can offer. Our next practice problem says the function f is given by f of x equals 50 times 1/2 to the power of x, and the function g is given by g of x equals 50 times 1/3 to the power of x. Here are graphs of f and g. Kieran says that since 3 is greater than 2, the graph of g lies above the graph of f. So graph 1 is the graph of g, and graph 2 is the graph of f. Do you agree? Explain your reasoning. So what I would say is that while 3 is greater than 2, 1/2 is greater than 1/3. Okay, the growth factors here are not 2 and 3. The growth factors here are 1/2 and 1/3. So, since 1/2 is greater than 1/3, f of x is staying bigger than g of x. This means graph 1 is f of x, and graph 2 is g of x. So we have to be careful when we're talking about these growth factors. If I see fractions, I'm not comparing the denominators to each other. I'm comparing the whole fraction. And in this case, 1/2 is greater than 1/3. That means 1/2 is going to remain larger, and therefore f of x must be the graph on top and be graph 1, whereas graph g is going to decay quicker. It is going to be the graph on the bottom, graph 2. If you have any questions about how to solve this problem, please leave a comment below, and I'll get back to you with any help I can offer. Our last practice problem says the function f is defined by f of x equals 50 times 3 to the power of x. The function g is defined by g of x equals a times b to the power of x. Here are the graphs of f and g. So we can see that the red line is f and the blue line is g. So number 1 asks us, how does a, the starting amount for g of x, compare to 50, the starting amount for f of x? So if we look, we can see that f starts lower than g. So we could say, since f starts lower than g, a is greater than 50. We don't know what a represents. All we know is the starting point for the blue line, which represents g, is above the starting line for the red line, or the starting point for the red line, which represents f. So if the starting point for f is 50, the starting point for g must be higher. Number 2, how does b compare to 3? Well, this means 3 is the growth factor, and B is the growth factor. And we can see that even though F starts lower, it quickly overtakes G. That means F is growing faster. So, since F is growing faster than G, B must be less than 3. We're not sure what it is, but we know the growth factor for F has to be larger because F is growing faster. So we know that B must be less than 3 since 3 is the growth factor for F. If you have any questions about how to solve any of these practice problems, please leave a comment below and I'll get back to you with any help I can offer. Before we finish up this lesson, I want to go back and take a look at the learning targets and make sure that you are where you need to be set up for success moving forward to future lessons. So we had 2 learning targets for this lesson. Number 1, I can explain the meaning of the intersection of the graphs of 2 functions in terms of the situations they represent. So you need to understand that if the 2 graphs intersect each other, at that point they are equal. It also helps you understand that, like the last practice problem, we could see where function G started higher than function F, but then we could see that function F crossed over function G. So we knew it had to have a higher growth factor. And so that intersection point is where function F overtakes function G. So this might come up in something like investing. Maybe there's 2 different investments, and you can see where even though one investment might start out higher, you can see the one that started out lower grow faster and overtake it, making it a better investment. Something like that. And then learning target number 2, when I know 2 points on a graph of an exponential function, I can write an equation for the function. So we have learned 2 different ways to do this. One way is if they give you consecutive points on the graph, because then you can take the second y, divide it by the first y, and it will tell you the growth factor. And then all you need is the initial starting point and the growth factor to write your equation. The other way that we explored in this lesson was if you have 2 points that are not consecutive, you need to use the coordinates for the points that you have to fill out the information you know in the exponential equation, and then divide the second point equation by the first point equation, and then solve to find B. Once you find B, then you can work on finding the initial amount, and once you find the initial amount, you'll be able to write the equation for the function as a whole. If all of this makes sense to you, then you're right where you should be. If you still have questions about any of this, please leave a comment below, and I'll get back to you with any clarification I can offer. If you found this video helpful, I ask that you please subscribe and give this video a thumbs up. And I look forward to seeing you in the next lesson.